Jenna Whalen. I am from Ms. Vaughn's first period, and I'm going to be talking about the 6 different laws that I learned during distant learning.
The first law that we are going to be talking about is Boyle's law. It states that at a constant temperature, which is in Kelvin, the volume being in milliliters/liters of a given mass, moles or grams, of a dry gas is inversely proportional to its pressure, millimeters of mercury, in atmospheres. Robert Boyle was a physicist who published the law in 1662. He showed how the volume air decreased was in exact proportion to its pressure produced by the liquid in the long part of the tube in his experiment. An example would be like spray paint, and how the intense pressure inside the can pushes outward on the liquid inside the can, trying to escape and forces the liquid out when the cap makes an opening. Here is a video of practice problems. I knew that this problem was Boyle's law because it gave me the initial volume and then the volume after it was compressed, and gave me the pressure after it was compressed, and wanted me to find what the initial pressure was. The temperature also stayed the same. When solving for this problem, you need to convert pascals to kilopascals. So then the 400 pascals turns to 0.4 kilopascals, because that is what the answer is going to be in at the end. To do that, you divide the 400 pascals by 1,000 kilopascals. After converting, you are going to use the equation P1 times V1 equals P2 times V2. Then plug in the 400 milliliters for the initial volume, and then on the other side, plug in 0.4 kilopascals for pressure after compression, and then 0.460 milliliters for the volume after compression. After multiplying, you should get P1 times 400 milliliters, and on the other side, 0.184 kilopascals/milliliters. Then you divide by the 400 milliliters to get P1 alone, and after dividing the milliliters, will cancel out, leaving you with the answer of 0.00046 kilopascals. Here is a video of me doing the practice problems.
So we're going to be doing Boyle's law today, and it states that as the volume goes up, the pressure goes down, or if the pressure goes up, then the volume goes down, and the temperature stays the same. So for this experiment, you're going to be needing a plastic water bottle, a thumbtack, 2 balloons, and scissors. So what you're going to do is you're going to take one of the balloons and you're going to cut it in half about, and then you're going to take your thumbtack and you're going to poke a hole at the bottom of the water bottle. And I already made a hole since it's tougher plastic, so it took a lot of strength to do it. So then what you're gonna do is take one of your balloons and you're gonna stick it in there, like so. And then you're gonna wrap it around on the top, so then it should look like that. And then on the bottom, you take your other balloon and you just wrap it like that. Oop. Let's do that again. So just, okay. So then your whole thing should look like that, balloon inside with the hole in the water bottle and then the balloon. And then what you're gonna do is you're gonna hold on this. Now doing this, the volume increases, which makes the pressure decrease, which makes the balloon go. Oh my goodness. But okay, as you can see, it has blown up a bit, and yeah.
The next law we are going to be talking about is Charles' Law. It states that the volume, which is in milliliters/liters of a gas, is directly proportional to the temperature in Kelvin. This law is valid as long as the pressure in millimeter of mercury or atmospheres and the amount of gas are constant. Jacques Charles did experiments on how the volume of gases depends on the temperature in 1787. Gay-Lussac was a scientist who made the definite measurements and published results showing that every gas he tested obeyed this generalization. The equation is V1 divided by T1 equals V2 divided by T2. An example in real life would be leaving a basketball out in the cold weather. When a basketball is left in the cold garage or outside during the cold months, it loses the air inside, or volume. This is showing with constant pressure. If the temperature drops, the volume decreases also. Here is a video of Charles' Law practice problems. I knew this problem was Charles because the pressure stayed constant and it gave me the initial volume and the initial temperature, and then gave me the temperature after it was cooled, and we are looking for the volume after it cooled. To solve it, I used the formula V1 divided by T1 equals V2 divided by T2. I first had to convert the 37 degrees to 310.15 Kelvin. So then, at the end, I could cancel the Kelvin and be left with liters for the volume. So then, I plugged in 3.4 liters for initial pressure and 400 Kelvin for initial volume. Then on the other side, I put a question mark for the volume after, since we are trying to find that, and then 310.15 Kelvin for the temperature after it cooled. After cross multiplying, I got 1054.51 Kelvin / liters divided by 400 Kelvin. The kelvins would cancel out, and I got the answer of 2.6 liters. Here is a video of me doing Charles' Law experiment. Okay, so for Charles' Law, it states that when the temperature rises, the volume will rise. I don't know why I'm doing this. When the temperature rises, the volume will rise. And that the pressure stays the same. So what you need for this experiment is a glass, bottle, and that I chilled for about 5 minutes because you're changing the temperature, and then a balloon and hot water. So then what you're gonna do is put the balloon over like that, and as you can already tell, it's already a little bit going up. So then you put it in, and it should, since you are changing the temperature from being cold to warm, that the volume will rise, which will cause this to more air up. You really see how it's rising. Hey! Look at that. It stood up. Science. And that is Charles' Law. Now what I'm going to do is stick it in the freezer for about 5 minutes, and we can see how, because the temperature goes down, volume goes down, it's taking up less space. So I'm gonna stick this in the freezer real quick. Okay, so we can see that after about a couple, 3-5 minutes about being in the refrigerator, it has gone down. And then probably if I kept it in there for 5-10 more minutes, probably would have been, the air probably be all the way out. But it's because since the temperature went down, the volume went down, and there was less happening inside the bottle, which caused the air to
delete that blue.
Our next law is Avogadro's law. It states that the volume in milliliters/liters of a gas is directly proportional to the amount of gas. The typical amount of gas is in moles. Avogadro's law assumes that the temperature in Kelvin and pressure in millimeters of mercury, or atmospheres, are constant. Avogadro said that the best explanation for Gay-Lussac's observations of gas reactions was that equal volumes of all gases at the same temperature and pressure contain equal numbers of molecules. The equation is V1 divided by N1 equals V2 divided by N2, and N being moles. A real-life example would be how spray bottles are advertised to be placed away from sunlight. This is because the volume of gas particles increases when the temperature is increased, and therefore the spray bottle can burst. Here is the practice problems for Avogadro's law. I knew that it was Avogadro's law because the temperature and volume stayed the same, and it gave us the initial volume and the moles, and it gave us what was left in container, and we had to find the volume. Before solving, I had to convert 30 grams to 0.68 moles to cancel the moles out at the end to be left with liters. To solve this problem, you use the equation V1 divided by N1 equals V2 divided by N2, and plug in 25.5 liters for initial volume and 3.5 moles for the initial moles. Then on the other side of the equation, put a question mark for the volume after the leakage, because that is what we are finding, and then 0.68 moles for the moles after leakage. After solving, the moles would be canceled out, leaving you with the answer of 4.95 liters. The next law we're going to be talking about is Gay-Lussac's law. It states that the pressure in millimeters of mercury, or atmospheres, of a given mass of gas varies directly with the absolute temperature of the gas when the volume is kept constant. Gay-Lussac discovered it by building an air thermometer when he discovered that the relationship between the pressure and temperature of a fixed mass of gas kept at a constant volume in 1800 and 1802. The equation for Gay-Lussac is initial pressure divided by initial temperature equals the pressure after the reaction divided by the temperature after the reaction. Some examples would be the rupture of pressure cooker, an aerosol can, and a tire, because all these substances explode when exposed to higher temperatures. This is a video of practice problems. In this problem, I knew it was Gay-Lussac's law because it gave me the initial pressure, the initial temperature, and gave me the final temperature. Also, the volume stayed constant. Before solving, you have to convert the 30 degrees Celsius to 303.15 kelvins, so that at the end, the kelvins can cancel out to leave you with millimeters of mercury. Then use the equation P1 divided by T1 equals P2 divided by T2, and put 67 millimeters of mercury for initial pressure, 87 kelvins for initial temperature, and then on the other side, put a question mark for final pressure since we're trying to find that, and then 303.15 kelvins for final temperature. After multiplying, I got 20,311.05 millimeters of mercury per kelvins divided by 87 kelvins. The kelvins will cancel out, leaving you with the answer of 233.46 millimeters of mercury. Here is a video of me doing an experiment for Gay-Lussac's law.
Okay, so for Gay-Lussac's law, you're going to need a pan with water in it, a candle, a spoon to stir around the food coloring just so you can easily see the water more clearly, and then like a jar or base, or something to put over the candle, and then a lighter. So put the food coloring in. And then put the candle in the middle, use the lighter. And so what the flame is going to do is, after I put then this over it, the flame excites the air molecules, which then they want to push away. And so that the air molecules are trying to expand in volume. As we can see here, that the water filled up higher because when the candle burned, it uses the air molecules. Yeah, so it uses the air molecules and it then forms combustion, which so it forms combustion, which is carbon dioxide, carbon monoxide, and water vapor. So then the combustion rises to the top, back away. You can't even really see that. So then the combustion rises to the top of the glass and the air to the bottom, and then soon there's no more air, so then the flame goes out. And so then the pressure then rises, and when the pressure is rising, it causes the water from the glass to try and equalize the pressure on the outside to the inside. So then it fills, so then it sucks up the water, causing it to be higher because it's trying to equalize the pressure. Because the air is cooling, so the outside wants to have the same pressure as the outside, which then causes it to bring in the water. That is Gay-Lussac's law.
The next law is combined gas laws. It states that the ratio of the product of pressure in millimeters of mercury in atmospheres and volume in milliliters/liters and the absolute temperature in Kelvin of a gas is equal to a constant. It combines Boyle's, Charles, and Gay-Lussac's law. The equation used is initial pressure times initial volume divided by the initial temperature equals final pressure times final volume divided by final temperature. Here are practice problems for combined gas laws. I knew that this problem was combined gas laws because it gave me the initial pressure, volume, and temperature. Then it gave me the final pressure and final temperature, and we are looking for the final volume. Before solving it, we need to convert the 30 degrees Celsius to 303.15 kelvins, the negative 80 degrees Celsius to 193.15 kelvins, so then the kelvins would cancel out at the end, and then 610 pascals, 2.006 atmospheres, so then the atmospheres will cancel out. Now we can use the equation and plug in 0.544 atmospheres for initial pressure, 7.0 liters for initial volume, 303.15 kelvins for initial temperature, and then on the other side put 0.006 atmospheres for final pressure. Leave V2 because we are trying to find that, and then 193.15 kelvins for final temperature. After multiplying and then cross-multiplying, you should get 735.5 atmospheres per liters per kelvins divided by 1.82 atmospheres per kelvins. The kelvins and atmospheres will cancel out, leaving you with the answer of 404.12 liters. Here is a video of me doing an experiment using combined gas laws.
Okay, so this is for combined gas law, and so what you'll need is like a cup, like a glass jar like this, a boiled egg, a lighter, and some paper. And so what's gonna happen is I'm gonna light this, put it in there, and then I'm gonna stick the egg immediately over it, and then the egg is gonna go in, because when you put the egg in and like over here, it causes the rise in temperature and pressure since there's fire in there, and it causes the egg to jump, releasing air, yeah, air and So then the pressure outside is more than the pressure inside of here, which causes the egg to then drop, which I'm going to demonstrate right now. Okay, so this is a closer view. Stick that in there, go. And then as you can see, it is dropping, and the air is out, and then plop, there it goes. Okay, so using the same concept, you should be able to push this back out and safety. Flip it. And then the heat is gonna push it right out. Ooh. Pop. Thank you.
So our next and final gas law is ideal gas law. It states that the pressure in millimeters of mercury or atmospheres, and the temperature in Kelvin, and the volume in milliliters or liters of gas are related to each other. The equation used is pressure times the volume equals the amount of substance times the ideal gas constant times temperature. This is a video of example problems. I knew that this was ideal gas law because the problem gave me the pressure, volume, and temperature. We are trying to find the mass, and there was no initial pressure and final pressure, or initial volume and final volume. Before solving, you will need to convert 36 degrees Celsius to 309.15 kelvins to cancel out the kelvins in the beginning. You will also need to convert the 1,325 millimeters of mercury to 1.74 atmospheres to be able to cancel out the atmosphere at the end, and then convert 1.03 moles to 28.85 grams at the very end, because we want our answers to be in grams at the end. To solve, we plug in 1.74 atm for pressure, 15 liters for volume, and then on the other side, we plug in 0.0821 liters per atmospheres per moles per Kelvin, because this is R, and then 309.15 Kelvin. After multiplying the equation, then it should look like 26.1 atmospheres per liters equals N times 25.38 liters per atmosphere per mole. Then you divide by 25.38 liters per atmospheres per mole at the other side, so N can be alone. The atmospheres and liters would cancel out, leaving you with 0.03 moles. For the final answer, we want it in grams, so then you would have to convert to grams, giving you the answer of 28.85 grams. So the last thing is common conversions. These are some conversions that I use to solve the equations for the different gas laws. And these are the sources that I use to help me discover more about the 6 different laws.